In this video, let us try to understand the merge sort as well as insertion sort and the trade-off in between these two algorithms. Even though they are sorting algorithms, they have their own benefits. So it's not that it's always necessary for you to use merge sort just because its time complexity is less than insertion sort. Both have their own advantages and disadvantages. So let us discuss about their trade-offs in this video. So talking about merge sort, the total complexity is O of n log n. And about the insertion sort, the total time complexity is O of n square. Now obviously looking at this time complexities, you would tell that insertion sort will always be outperformed using merge sort. But believe me, it's not the always. I mean, it's not the case always. So even though this is greater than this, but in some cases, insertion sort will outperform merge sort, and I am going to show you how will it happen. Okay, let us discuss about the performance of merge sort first. So what does the merge sort do? Given an array, let us say, given an array, it will break these arrays into subarrays. And it will break these into subarrays. Just think that this is 8 cells, these are 4 cells, and these are 2, and this will be broken into 1, 1, 1, 1. So this will keep on breaking the and it will keep on breaking the array into subarrays until it reaches a unit space. So what is a unit space? Basically, unit space is a single cell. Okay, so after this, what will this algorithm will do is it will try comparing these two elements at a time. So it will try comparing these two elements, and the greater elements will be placed on the right side, whereas the smaller element will be placed on the left side. So okay, maybe this is A and this is B. Previously this is B and this is C. And this happens recursively. So this is the recursive call 1, this is recursive call 2, this is recursive call 3, and in the recursive call 3, on returning back to the recursive call 2 in the recursive stack, it will try comparing these unit elements and it will return back to the recursive stack. And after this, recursive call will be passed on to recursive 4 on the left side. So it is left first, on the left first, then the right. So this is how the recursive stack will be designed in the stack, in the RAM basically. And now after the recursive call 4, it will compute these both subarrays. Maybe this is C and D, and it will return to the recursive stack R4 call, and R2 and R4 will be returned to R1, where it will compute these both subarrays. If everything is fine, then well and good. It will just try to compute between A and B. It will make sure that these numbers fall in right place, or maybe these characters fall in right place. So it will just try to copy this, and it will make 4 cells because it's getting 4 and A. Then it will try to compute the right part. If everything is well, it will just copy. If not, it will try to adjust those characters and it will place them in order, and this will be returned back. So if you observe, it is going to do this for every subarray, and it will merge this. So because it is breaking from 8 to 4, from 4 to 2, from 2 to 1, it is like a binary tree. So thinking of binary tree, the subarrays will be generated at the time complexity of O of log n, and this is base 2. But because we are doing it for n elements, this will be multiplied by O of n. The final complexity will be O of n log base 2 n for every unit element in the array. But just think of, what if the array given is already sorted? Just think of what if the array given is already sorted. It will perform all these steps in spite of the array being sorted. So we are simply wasting O of n log n time complexity just to sort the array which is already sorted. But on the other hand, just think of insertion sort. Let me draw the time complexities first. O of 1 is smaller than O of n. This is smaller than O of n log n, and this is lower than n square. Okay, now obviously this here log n, and this 2n. Okay, so let's think of insertion sort. Insertion sort basically has two for loops. First for loop from I to n, and the second for loop from j. This basically inserts elements in an order. So I'm not going to discuss in depth about the insertion sort, but I'm just giving you a brief idea about what the insertion sort does. So insertion sort manages to insert the elements in order. So this inner element will be executed only and only if it gets any other element which is not in the right place. So if the element is in the right place, then the inner for loop will not execute. So what I'm trying to say is, if the insertion sort gets an array which is already sorted, it won't get into the inner for loop, and it will exit by the complexity of O of n, because this won't be executed at all, and this will be running for linear time complexity which is O of n. In the sorted array case, merge sort was outperformed by insertion sort, because in insertion sort we won't be going into the inner for loop. It is based on the condition. Now, so you decide, is insertion sort better or merge sort better? Previously you had an answer that the merge sort is better than insertion sort, but now because of the sorted arrays, you might have a different opinion, completely different opinion on the insertion sort. But wait for a second. What I'm going to introduce now is the hybrid sort. Hybrid sort is such a sort that it switches in between these two optimized algorithms just to maintain the time complexity, that too keeping the time constraint onto the point. So what happens in this merge hybrid sort is, on the smaller number of if you take large amount of arrays, so larger amount of arrays, on the larger amount of arrays, obviously insertion sort will be outperformed. So large arrays merge, on the smaller arrays use insertion. Why? Because just think of performing O of n square time complexity on the large array and O of n log n time complexity on the smaller arrays. Obviously, if you perform O of n square on the larger arrays, the time complexity will be exponential. But for the smaller arrays, if you perform merge sort, for the smaller arrays, if you are performing merge sort, then the thing that it would happen is merge sort also needs stack. It also needs memory, whereas insertion sort does not. I mean, it doesn't need any memory. Merge sort needs memory because it uses the recursive stack first of all. So along with n log n time complexity, it also uses memory. So this is a trade-off between insertion sort and merge sort. Now, so okay, I have concluded that for smaller arrays you need to use insertion sort, whereas for the larger arrays you need to use the merge sort. But how to come up with an optimal value? How did I come up with an optimal value just to decide whether the array is larger or smaller? Based upon my experiments that I have performed previously, I have concluded that 65 is the maximum threshold for using the insertion sort, and if the array size is greater than 65, then you have to switch to the merge sort, and this is basically a hybrid sort. Now I'm going to discuss about the code as well. If you see here, see switches in between insertion sort and merge sort. Okay, if you look at the graph, the blue line is merge sort, whereas the red line is insertion sort, and this area is around 65, and these are nothing but the sizes of the array. These are the sizes of the array that I have experimented on. So if you look at the point 65, insertion sort was performing very well. Insertion sort, the red line is below the blue line and it was performing very well. But right when it reached to 65, it rose exponentially, whereas merge sort is showing consistent performance. So keeping this in mind, I have concluded that 65 is the right point, right threshold that your algorithm has to switch in between from insertion to merge sort. Because insertion is performing well until 65 and then merge is performing well after 65, which is threshold of an array. So okay, let me write the pseudocode for this. Coming to the pseudocode, maybe you can use Python def hybrid sort. For hybrid sort, you need to pass in the array, and yeah, just the array. Okay, now first we have to compute the length. Length equals to size of array if length is greater than 65, means it is larger than the threshold. Threshold is 65 here as per the experiments that I've done. If it is greater than 65, it has to switch to merge sort, but if it is less than 65, it has to keep going with the insertion sort. So if it is greater than 65, it has to merge sort on array, else it has to perform insertion sort. Insertion sort on the array. I'm going to show the code of merge sort as well as insertion sort. So just get a brief idea about this. Considering the length, we need to switch in between merge and insertion sort. This is basically hybrid sort. That's it. And at last, we need to just return the array. That's it. And okay, now I'll show you the merge sort as well as insertion sort code. I've coded this in Java, and as well as I did this in Python. So yeah, I'll discuss this in Python. Maybe it would be easy for you to understand. Yeah, so this is the main line of the code from where the execution starts. So this is an object for the hybrid sort, and this is an object for the sorter. Sorters are basically, what are these? The sorters are the insertion sort and the merge sort. Okay, it contains the two sorting algorithms, and these are the arrays. Okay, I mean, this is a singular array. Now I have calculated the length of the array, and I also calculated the threshold. Now I'm just using the sort method, which is an hybrid sort, and I have passed in the array and the size of the array along with the threshold and the sorters. Sorters are basically those two algorithms that are being used. So on calling this, it will call this class, this method. Basically, it will try to call this method, and see, if n is nothing but the length of the array. If it is less than k is 65. If it is less, then it will go to insertion sort, whereas if it is greater than 65, it will go perform merge sort. That's it. And then at last it will return the sorted arrays. So this is the code for insertion sort. If you look at this is the code for insertion sort, where we are trying to compute the sorted numbers, and this is the first for loop, which will run for O of n times, and this is the second for loop that will run for O of n times. But because this is inside another loop, it will go O of n squared times. And if you observe, if at all, if this condition is not matching, if this condition doesn't match, it will never ever enter in this loop, and this exact condition will be triggered when, or should I say will not be triggered when, the array is already sorted. Okay, so this will not be triggered when the array is not sorted. Thus, it won't enter this block at all, and it will make the complexity as O of n, which is obviously greater than, I mean, it is less than O of n log n. So insertion sort at this point of time will outperform merge sort, and if it is triggered, then obviously it will get in, and it will perform for O of n square times. Talking about the merge sort, see, merge sort is very simple. I say very simple. We are just trying to break the arrays into subarrays. Then, while combining these units, it will get little harder for you, because the code looks like condition 1 and condition 2. If these both conditions are satisfied, then we have to make shifts in those subarrays. Like if I have this as a subarray and this is a subarray, 3, 4, I need to keep an eye on I and j. I have to make sure that I is always less than j, then only I can put these elements, let us say x y, z and a. If at a point where I gets greater than j, then I need to make shifts and copy whatever the value is less. I mean, if the value of I is greater than j at some point, then I'll copy the i's value. Then I'll try to copy. I mean, wait. If I is greater, then I'll try to copy the j's value first, and then I will copy the i's value. So these are the shifts that I'm making. If this is less than the right part, then I will simply append, else I will append the right parts, whatever I've explained previously. So this is how I merge to and return. So yeah, this is basically about the hybrid sort. I hope you understood this very well, and